Hey guys, I'm back with another related rates problem. This time we'll be going through the shadow problem. The shadow problem is one of those problems that is usually considered by people taking calculus for the first time. It's a very complicated problem because it isn't the derivative that's very complicated, but they're seeking the relationship. And that's usually the hardest part of most related rates problems, is finding the relationship. And the shadow problem is a very subtle relationship, I guess you could say, especially from the perspective of people taking calc from the first time. So in addition, it also has this, this kind of shock factor, you could say, because what the question is asking you to do doesn't seem very, it's not the first application of calculus you'd think of naturally, as compared to, filling a tank with water. So let's get into the shadow problem. So a 2-meter man walks away from a 6-meter lamppost at 2 meters per second. The lamp casts a shadow in front of the man. How fast is the head of a shadow moving? Now, like I said, this isn't, an application you really think of when thinking of calculus, but here we're given this problem where we need to find how fast the head of this man's shadow is moving. So, like all other related rates problems, it's very, very good to draw the situation, and especially for this one, draw the situation. I can't emphasize that enough. Otherwise, you won't be able to figure this problem out. So, I'm going to draw the man. So, he's fairly tall. He's 2 meters tall. And there he is, represented by the line. And so, let's also draw the lamppost. We're just filling in the information we know. So, we got this lamppost. Got a light at the top. And this is 6 meters tall. So there's a light up there. And, well, this light's going to hit the back of the man, and it's going to get blocked and cast a shadow in front of him. So, let's draw the light. It's going. Hits him, hits his head, and it casts a shadow right there. Let's say this is where the head of his shadow is. The head. And obviously this is just the ground. Draw a line there. And, well, what are we given? Well, we're given that this man is walking at 2 meters per second from the lamppost. And we could think of this on lamppost as the origin. If I put this on a Cartesian plane, this would be the origin. So we could say the man's distance from this origin. If he started right at the base of the lamp, we could call this distance x. And we can call this distance where the man's head is, or the head of his shadow is actually. We can call this distance, L. So now we've labeled our diagram, and the first thing you see in this diagram is that you got this big triangle right here with a side of 6, and then also a side of L, and you have a second triangle as well, and that triangle is formed by the man and the distance from the man's feet to the head of his shadow, which is this. So we got 2 triangles here. This big one and we got the small one, and these are similar triangles, if you recall. They're basically, the larger triangle is just an upscaling of the smaller one. Just, they have the same ratio of the side lengths. So, well, the issue is that all we know is one side of each triangle. But even with that, let's write out what we've got so far. So let's start with a big triangle. So the big triangle has a side of 6 and another side, the bottom side, one side, as length L. Now what about the other triangles? Well, it has one side that is 2 meters, which is the man and his height. And, well, we don't exactly have the other side. We don't have this. But we can figure it out. See, the key to this problem is, always keeping track of what you have. And, a lot of students, they can get confused when they got, all these missing components. And it can really throw them off. So don't, lose your nerve, especially on a test when you got, all these terms. You got X, you got L, you got a bunch of numbers, and you don't see something obvious right away. Play around with it, and eventually you'll figure it out. So how do I figure out this length? I can write it in terms of X and L. There's nothing wrong with that. And what it comes out to is, well, just L minus X, right? L is the full, minus this is basically this, distance from his feet to the head of his shadow, right? So that's L minus X. Now I got an equation with I got L, I got X. I don't see something obvious right away. But, I can rearrange this, right? I can multiply sides, I can rearrange this, right? So if I rearrange this, let's get all the letters to one side, all the variables to one side, and all the numbers to the other. So I get 2 over 6, which is just, I'll just write 2 over 6 for now. And I can simplify this a bit more. Let's collect all the L's on one side and all the X's on the other. We only have one X and one L, and we got this constant, 2 over 6. So let's collect them. Let's separate these two. Let's separate L and X. So let's multiply L to the right side, and we get L minus X is equal to 1 over 3L. Let's add X to both sides and subtract 1 over 3L from both sides. So we get L minus 1 over 3L is equal to X. I'm just going to erase this. And what do we get? Well, now we just get 2 over 3L is equal to X. Pretty simple now. We've simplified, this expression, and we've gotten something, easier to work with. And what we've gotten is our relationship between, L and X, basically the two lengths that we needed, which was, we're trying to figure out the relationship between how fast the head of the shadow is moving, the rate of that, and the rate of change in X. We're given that. We're given how fast the man is moving, and we want to figure out how fast the head of his shadow is moving. And that distance from the lamppost is L. This was the head of his shadow, right? So we got that distance. We figured out this, this component, and we related them. All we need to do now is take the derivative, because that was what we're looking for. Remember, related rates problems. We have two quantities. We're given the rate of one, and we need to find out the rate of change in the other. So what we were given was how fast the man was moving, which was the change in X. And what we needed to find out was how fast the head of his shadow was moving. And the distance from the lamppost, the base of the lamppost, to the head of his shadow was L. So we needed to find how fast L is changing. So we've gotten a relationship. We had it right here. So we just simplified that relationship, and we came to it here. And all we need to do now is just take the derivative on both sides with respect to time. Doing that, I just get dl by dt is equal to not 0, but dx by dt. And just going to do some erasing up here. So understanding that, you know, related rates problems, you gotta draw the situation and then realize what quantities you're trying to figure out. What quantities are you trying to relate? And finding an equation for that. And we did that. We found an equation that related L and X, which was the two quantities that we were dealing with, the related rates, to find the related rates. These rates are related, so obviously related rates. And we found those two quantities, L and X. So here, we've taken the derivative on both sides. I'm just going to rewrite this now. So we got 2 over 3 dl by dt. And we know dx by dt. We know how fast the man is moving. And he's moving at 2 meters per second. So now it's just a matter of just isolating. And what we get is that dl by dt, which is how fast the head of his shadow is moving, is 3 meters per second. 2's cancel out. You multiply 3 meters per second. Not as hard as it seems to be when it comes to taking the derivative, but realizing this relationship can be, come across as very complicated. So you really need to understand what you're doing when you're figuring out related rates problems. You gotta figure out what you're doing. What does related rates mean? And always, always, always draw a diagram. So I hope this video helped. Thanks for watching. I'll probably post a few more related rates problems, more common ones, and work through them. If this helped, like and subscribe, and